what is the outgoing velocity of water in a container which a lateral opening. The point is, what is the outcoming velocity? Imagine you have a container of water, and I open an opening at one point, which is h length below the free surface of the water, right? We are wondering, what is the velocity at which the water should get out of the outgoing velocity? Can be computed. Why? Look, consider the container, okay? Let's imagine that this is a big container, okay? So this surface is much larger than the opening surface, okay? So S1 at point 1 is much larger than S2, okay? That's what we have here. Let's consider now a streamline. Okay, we can consider that, of course, as we are opening an opening in the lateral wall of the reservoir. Of course, water in the reservoir is moving down, right? But very slowly. So I can consider that if that is large enough, the body, the motion of particles here are a steady state, because the velocities are so small that not the velocity. The velocity in all here can be considered steady state. In fact, you can generalize that, and there is a problem in the book of problems in which this is done even considering that the velocity at these points, right? But let's, for the time being, assuming that this reservoir is so large, or this section 1 is so large, that first we can consider that the velocity here is 0. So the down velocity of particles here is almost negligible. Second, let's identify a streamline. Of course, there are particles that are moving towards that situation. Of course, there are some particles. And in particular, we don't know exactly where the streamline is, but we know that there is some streamline that goes from here to the upper surface. Okay? We don't need to identify precisely where is it. We just know that there is one streamline going from here to here. So this is a streamline that could be identified also as a path line. And then this is water, so perfect fluid. This is a steady state, approximately. Then what else? It's gravitational forces. So we can apply the Bernoulli's theory. So let's apply that. So let's consider the Bernoulli's trinomial at point 1 at the beginning of the streamline, and point 2 just at the end of the streamline, when the streamline gets out at the atmosphere, right? So let's consider the origin of coordinates here. So the elevation of point 1 is Z1, okay? The elevation, the pressure at point 1, what is the pressure at point 1? What would you say? What is the pressure here? Atmospheric pressure, maybe negligible, okay? And the velocity at point 1, what do you imagine is it? Almost 0, okay? So finally, at point 1, this trinomial gets reduced to the h. So that h is the constant value for all the points there. Now let's consider the end of the streamline, point 2. What is the elevation? Well, if we take this as the reference, elevation is 0, right? What is the pressure? Well, this is known. For instance, if that is an opening to the air, which is the case, the pressure is atmospheric pressure. And then the velocity, well, that's what we want to compute. So finally, doing that, we have that Z1, which is h, equals Z2, which is 0, plus the velocity divided by the g. And then we obtain this formula. The velocity, V2, at the outgoing water point is equal to the square root of 2 to GH. And that's it. That's a formula that appears in thousands of handbooks to determine what would be the outgoing velocity of water from a lateral site opening into in a large reservoir. And that's used for designing many things. That can be made a little more sophisticated, even considering that this, not considering that the velocity is 0 here. And there is a problem in the book of problems that is that. But look at that. By the way, does this formula recalls you something, reminds you something? What is that? What is the velocity of an object which is dropped from a certain point when it has moved due to gravity a distance h? It's the same. They have nothing to do, but it's the same formula. It's like if you just leave some object here, and when it arrives to here, it arrives at the same velocity that the water is coming in here. And look, that velocity is independent of the size of the opening. Whenever, I mean, it can be, it's smaller than but so it doesn't matter how big is the size, the velocity is always the same. Okay? The volume flow would be larger, of course, which would be the product of the velocity times the section of the opening. Okay?